Welcome to the remediation video for the unit that covers periodic trends, bonding, and molecular structure. In order to be able to participate in the remediation process, right now you're going to need to grab, first of all, your remediation invitation letter. You'll notice at the top of this letter there are 4 potential key concepts, central pieces of information that you need to understand, the essentials. And we have placed check marks next to the information that, based upon your test performance, it looks like you did not fully comprehend having taken the test once before. So the hope is that if you look over this invitation letter, you'll be able to identify the concepts that you need the most help with, understanding that this remediation video covers all of these concepts, and when you take the remediation retest, you'll be tested over all 4 of them, regardless of which sections of them you did not specifically understand. So you'll need your invitation letter. You'll also need your periodic table, of course, because everything we're doing relates back to your table. Then you'll need note-taking materials, and then also the assignment that was posted with this video. Understand that in order to get into the remediation sessions that are coming during Pride, you will need to have both notes from this video and then also that homework assignment completed. And please remember that the answers to that homework assignment are posted, and the expectation is that you're not only doing the assignment, but you're checking your answers. And if you have questions about why you're still getting some of these answers wrong, please be sure to get those questions answered either outside of class time or during the Pride remediation session. So if you do not have all of these things pulled together yet, please hit pause in the video, gather these things together, and then hit play when you're ready to go. Now that you have all of the information pulled together that you need in order to participate in this process, we are now going to look first at the information that we're going to cover over the next few minutes. So in order, the first thing that we're going to do is we are going to talk about how to identify whether substances are salts or molecules. We'll be doing this by relating it to the periodic table and their properties as metals and nonmetals. After that, we're going to talk about how to identify electronegativity relationships in compounds. We're going to find that this is going to be very important in the coming units and something that you need to be able to do. After that, of course, it's important that you know how to draw Lewis dot molecular structures, and we'll go back over that. And then finally, you'll need to be able to identify the 3-dimensional structures of these molecules based upon their Lewis dot structures. You'll notice that we have not included the specific names or angles for these molecules. While it is helpful to understand the names and angles, it's not critical that you know these, and you will not be tested again on the names and angles. You'll merely need to be able to draw their Lewis dot molecular structures and then identify what these look like 3-dimensionally. Okay, getting started and talking about identifying salts and molecules. A substance, a compound, is a salt or a molecule depending upon the atoms that make it up. And as you may remember when we went over the trends and parts of the periodic table, the periodic table is loosely broken into 2 sections. The majority of the periodic table on the left, as shown here by the blue boxes within the circle, these are the metals. Most of the periodic table, most of the elements are metals. The heavy blue line that stair steps through the right-hand side of the periodic table separates the metals from the nonmetals. And if we remember, these metals are weak and they tend to be electron losers. In class, we talked about the idea that they were big and weak and electron losers. But it's important for you to understand that the metals, the elements on the left, are weak and they tend to lose electrons. In contrast to that, over here on the right, the elements that are colored in green, these elements are the nonmetals. From class, we talked about the idea that they are small. And while that's true, it's important that you understand that these elements are strong and they tend to be electron gainers. We're not going to worry about the metalloids, the elements that are given in red. What you need to understand is that the elements on the left are the metals and they are electron losers, and the metals on the right are the electron gainers. Metals are weak, nonmetals are strong. From this, we can then figure out the types of compounds that these elements form when they get together. So the first type of compound that we are going to talk about are what are called the salts. Salts form when one element steals from another, creating ions. So in order for electron stealing to take place, first of all, we need an element that easily loses electrons. Those would be the metals, because they are weak and they tend to lose their electrons. And when a weak metal gets together with a strong nonmetal, as you might expect, the strong nonmetal is able to steal electrons from the weak metal. As a result, the metal becomes positive, the nonmetal becomes negative, and those positive and negative charges attract, and we end up with ionic bond formation, which then results in salts. So anytime you have a metal bonding with a nonmetal, those will form salts. Now, the one exception to this is hydrogen. While hydrogen is technically a metal, you'll notice that it's colored green. The reason that it's colored green is because it actually tends to react as if it were a nonmetal. In class, we talked about the idea that hydrogen is an unusually strong metal, and as a result, it doesn't tend to lose electrons, so it reacts more like a nonmetal. So now let's talk about nonmetal reactions. So now we are done talking about the metals, and let's focus on the nonmetals, including hydrogen. So when two nonmetals get together, remember that nonmetals are strong and they tend to gain electrons. Well, when you get two nonmetals together, they start pulling on each other's electrons, but because they are both strong, neither one is able to steal from the other, and these atoms end up sharing. When these atoms share, they form a different type of bond called a covalent bond, and these covalent bonds lead to what we call molecules. So anytime we have two nonmetals bonding together, these will share electrons and they will form covalent bonds and molecules. So from all this information, what you need to be able to do is, given any compound, you need to be able to determine if that is a salt or a molecule. So for example, if we look at a compound like carbon dioxide, we see that carbon is a nonmetal, we see that oxygen is a nonmetal, and when we have two nonmetals bonded together, we know that this will form a sharing bond or a covalent bond, and what you need to know is that this is a molecule. So anytime you have two nonmetals bonding together, that will form a molecule. Now, let's take a look at another compound, our familiar friend, table salt. Now we have sodium, which is a metal, and chlorine, which is a nonmetal. Again, as we said earlier, the metal is weak, the nonmetal is strong, and the chlorine will steal electrons from the sodium. That creates ionic bonds, and that forms a salt. So here, anytime we have a metal bonding to a nonmetal, that will form a salt. So looking at one more example then, we have the example of water. And we see that oxygen is a nonmetal, and we see that hydrogen is a metal. And when we see that, our initial thought is that's going to be a salt. But it's important for us to remember that hydrogen, while it is a metal, is unusually strong, and as a result, we think of it as being a nonmetal. So what we really have here is two nonmetals that are bonding together, which makes water a molecule. So in summary, salts are formed by a metal bonding with a nonmetal. Molecules are formed by two nonmetals bonding together, and in that we treat hydrogen as if it were a metal. So that is one of the 4 things that you're going to need to be able to do for the remediation test, is given the formula for compounds, you've got to be able to identify them as being a salt or a molecule. The next concept that you need to understand, or the next skill that you need to have, is the ability to identify electronegativity relationships in compounds. So to refresh your memory, it's important to remember that electronegativity is a measure of an atom's ability to steal electrons from other atoms. We care about this because it helps us understand the types of bonds that will form in these compounds. A simpler way, though, to think about electronegativity is to think about it as stealing power. It's literally an atom's ability to steal electrons from other atoms. When we look at the periodic table and we try to find the electronegativity relationships between the elements on the periodic table, we talked about in class the idea that as we go down a group, the elements get weaker. From this periodic table, you can see that the height of each one of these boxes is representative of electronegativity, and as we go down, the elements get weaker. Then notice as we go from left to right across a period, these elements actually get stronger. So what that means then is that the weakest elements on the periodic table are in the bottom left corner, and then the strongest elements are in the upper right-hand corner. Now, what you need to be able to do is you need to be able to identify the stronger element in a compound. And you can do this by remembering the trends that it goes from bottom left to top right, as we've said, from weaker to stronger. However, there's a more surefire way to figure out which element on the period or within a compound is stronger. What you can do is simply grab your periodic tables and flip them over onto the back. And when you flip them over onto the back, you'll notice in the key in the lower left-hand corner that electronegativity is the number in the upper right-hand corner of each one of the cells of the periodic table. So if you need to be able to identify which element in a compound is the more electronegative, all you simply have to do is look them up on the periodic table and compare. So for example, looking at the examples that we did previously, if you have carbon dioxide, looking on your periodic table, you'll notice that oxygen is to the right of carbon, and given the trend that they get stronger to the right, that would make oxygen more electronegative than carbon. So on the question, on the test, it would ask you which one is stronger, and you would simply say the one on the right, the oxygen. But if you didn't remember the trend, all that you would need to do is look these up on your periodic table, and you would see from our periodic table, not the one on the screen, but from our periodic table, oxygen has an electronegativity of 3.44, carbon is 2.55, and you can identify that oxygen is stronger than carbon just by looking up the numbers. Looking at the next example that we looked at previously, take a look at sodium chloride. Sodium is on the left, chlorine is far to the right, so we would expect chlorine to be stronger. But again, if you don't remember the trends, sodium off of our periodic table has an electronegativity of 0.83. Notice these numbers are different than the one on the table, and that's fine. Chlorine has an electronegativity of 3.16, telling us that chlorine is more electronegative than sodium. Then finally, the last one that we talked about a moment ago was the molecule water. We see that oxygen is to the right of hydrogen, and that would tell us that oxygen is probably going to be stronger. When we look up their electronegativities, oxygen is 3.44, hydrogen is 2.2, and we would then understand that oxygen is the more electronegative element. So those are the two abilities that you need to have relative to the periodic table in terms of talking about compounds. First, you've got to identify whether a compound is a salt or a molecule. You do that by realizing that metals and nonmetals make salts and 2 nonmetals make molecules. And then you've got to be able to compare their electronegativities. You can either do that by the trends, or the safest thing to do is to just look up their electronegativities on the back of our periodic table and then circle or identify the one that is strongest. So we're halfway done then with the things that we need to remediate. The remaining 2 actually have to do with molecules. In the last unit, you learned to draw the Lewis dot structures for molecules. Then initially you learned to count shared and lone pairs. After that, you learned to turn the shared and lone pairs into domain and molecular geometries and angles. And then we did a lab where you actually drew what these molecules looked like. Well, what we're going to do for remediation is actually the first and the last part. You need to be able to draw Lewis dot structures, and you need to be able to identify their 3-dimensional shapes. You don't, however, need to know the names and angles. We just need to know that you know what these molecules look like, because that'll be important going into the next unit. So let's remind ourselves how to draw Lewis dot structures. You may remember from class we gave you steps in terms of how to draw these structures. We'll go back over the steps and then we'll show you some examples. So the first thing that we will do is we will put all of the atoms on the paper and we will single bond everything together. As we're doing this, it's important to remember that these molecules tend to be symmetrical, meaning they are evenly distributed in space or the same on all sides, when they can be. So for example, if we have the molecule NO2, we could organize these with a nitrogen and then 2 oxygens, but we notice that that is not symmetrical. We've got a nitrogen on one side, and we've got an oxygen on the other if we divide it down the middle, and that is not symmetrical. Instead, we would distribute these symmetrically so that the nitrogen is in the middle and the oxygens are on either side, making the molecule more symmetrical. Once we've drawn this symmetrically, the next thing that we need to remember is that carbon, because it has 4 bonding sites, tends to be in the middle, and we'll put it there whenever we can. It's important that we remember this one, and this was a very, very common mistake that we saw in the first test. When you are drawing, when you're putting these atoms on the paper, make sure that you do not put halogens or hydrogen in the middle. The halogens are group 7. They include fluorine, chlorine, bromine, iodine, and astatine. These elements will not be in the middle of molecules because they have 7 valence electrons and only 1 bonding site. Not only, though, can't they be in the middle, they also cannot double or triple bond. The halogens and hydrogen can only form 1 bond, and that's going to become more important later, but for now, never put these guys in the middle. The next thing that we need to do then is we need to count all the valence electrons for every atom, and when we do that, watch out for ions. If we have an ion, it will change the number of valence electrons. Once we have all of this done, we will then spread any unused electrons, any unused valence electrons around the molecule. And at this point, it really doesn't matter where we put them, except for one very important point. The halogens have got to be filled with unbonded electrons. As we mentioned a second ago, the halogens only have 1 bonding site, so they cannot double or triple bond. As a result, you've got to fill them up first. If you lost points on your Lewis dot structures on the test, very likely this is one of the mistakes you made. And then fourth, you will check and fill octets by creating multiple bonds. So these are the 4 steps for drawing Lewis dot structures. If you've fallen behind in taking notes, hit pause, get these things copied into your notes, and when you're ready to go, hit play, and we will start drawing Lewis dot structures together. Okay, now we're ready to start drawing Lewis dot structures. The first example that we are going to do is NCl3. In order to do this, the first thing that we need to do is we need to put these atoms on the paper and we need to draw them as symmetrically as possible. Now remember that in Lewis dot structures, up and down and left and right are meaningless. So we can draw our nitrogen and a chlorine and a chlorine and a chlorine. Now understand, it doesn't matter if these chlorines are top, bottom, left, or right. We remember that there actually aren't any 90-degree angles in these molecules anyway, so it doesn't matter. So that would be step number 1. Now step number 2 is to add up all the valence electrons. In order to do this, we need a periodic table. So we find nitrogen, and nitrogen being right here has 1, 2, 3, 4, 5 valence electrons. So nitrogen has got 5 valence electrons, and we will write that down right above the N. Then we find chlorine. Chlorine is element number 17. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. So chlorine has got 7 valence electrons, but there are 3 of them. So that means a total of 21. Adding those up, we've got 26 electrons. Let's do this. So adding that up, we've got 26 electrons. Looking back at our previous picture then, we now need to figure out how many valence electrons we've already used. Remember that each one of these bonds counts as 2 electrons. So we have 2 and 2 and 2 valence electrons already accounted for on the screen. As a result, we have used already 6 total electrons, leaving us 20 more. So now it's time for us to put these 20 remaining electrons on the molecule. Remember what we said earlier though, we've got halogens. Chlorine is a halogen. So are all of these guys, but chlorine is a halogen. It can only form 1 bond, and it's already done that, so it's done. So we need to fill the chlorines first. So we will go 1, 2, 3, 4, 5, 6. Now that chlorine is happy. Then 7, 8, 9, 10, 11, 12. Now that chlorine is happy with 8 electrons. Then 13, 14, 15, 16, 17, 18. And that chlorine is now full. We've used now 18 of the 20 electrons, so we've got 2 more, and we can put those on the nitrogens. Now that we've done that, the last thing that we need to do is check for full octets. And in doing this, and you don't need to draw these circles, but to help you see what we're looking at, you'll notice that this chlorine is surrounded by 8 electrons. 2, 4, 6, and then the bond is 8. So that chlorine is full, and it's got its 8 valence electrons. You'll notice that on the right, this chlorine also has its 8 valence electrons. If you look down at the bottom, you'll notice that this chlorine also has its 8 valence electrons. And then finally, looking at the nitrogen also has 8 valence electrons, so everybody's got 8, and that would be the Lewis dot structure for NCl3. Notice that we do not need to worry about the names or the angles for this molecule. For now, all that you need to be able to do is draw its Lewis dot structure. Moving on then, let's take a shot at C2H4. Again, the first thing that we're going to do is we are going to get everything on the board. That means we've got carbons, and we learned a second ago that the carbons like to be in the middle, so we'll draw them like that. Then we've got hydrogens. We've got 4 of them, but rather than spreading them out 3 and 1, we are going to spread them out 2 and 2 to make these symmetrical. Now that we've done that, we've got all the atoms on the board, and it's time for us to take a look at valence electrons. Carbon, looking at your periodic table, has got 1, 2, 3, 4 valence electrons, but there's 2 of them for a total of 8. Hydrogen has got 1 valence electron, times 4 is 4, and that leaves us with a total of 12. Then counting the electrons that are already on the board, we've got 2, 4, 6, 8, 10. electrons on the board. So of these 12 electrons, we have already placed 10, leaving us with 2. So now we need to put these 2 electrons on the molecule, and the only place we can't put them is on the hydrogen, because hydrogen can only form 1 bond and then it's full. So we could put these 2 electrons on the left, or we could put these 2 electrons on the right. The thing that we don't want to do is separate them. We always treat electrons in pairs. So we'll leave the electrons on the right. So now it's time for us to check the octet rule. You'll notice that these hydrogens do not have 8 valence electrons. They don't want 8. They can only have 2. So once a hydrogen bonds, it's done. So then we look at our carbons. And if we look at the carbon on the right, we see that that carbon has got 4 sets of 2 electrons, and it is happy. But if we look at the carbon on the left, we notice that that guy's only got 6. So now we need to give the carbon on the left more electrons. In order to do that, we will take the 2 electrons off the carbon on the right, and we will push them into the middle, and we will form a double bond. And now, if we go and check octets, the carbon on the left has 4, the carbon on the right has 4, and that is the Lewis dot structure for C2H4. One more example. The last one that we need to do is a molecule with a charge. These are called polyatomic ions. You're learning about these currently in class, but we still need to learn to do their Lewis dot structures. So in order to do this, step number 1, get everything on the board, single bond it all together. Now we need, and remember top, bottom, left, and right does not matter, but what we need to do now is count valence electrons. Nitrogen is here. It is in group 5, so it's got 5 valence electrons. Oxygen is right next to it, group 6, times 3 is 18, and then remember the -1 charge gives us a bonus electron, giving us a total of 24. Now we need to count the number of electrons already on the board. We have 2, we have 4, we have 6. So of those 24 electrons, we have already used 6 of them. That leaves us a total of 18. So now we need to figure out how to get these on the board. And it does not matter where they go. We don't have any halogens to fill up first, so we can put them wherever we want. So maybe we'll start and we'll fill up an oxygen. 1, 2, 3, 4, 5, 6. So now we've used 6. Then maybe we go 7, 8, 9, 10, 11, 12, and then 13, 14, 15, 16. And that leaves us with 2 more electrons. And it does not matter where you put them. You could put 2 on the nitrogen and leave the oxygen on the right with 4. You could put 2 on the oxygen and not put any more on the nitrogen. It doesn't matter. You'll always end up in the same place. So we'll just leave these electrons on the oxygen on the right. Now when we check octets, this oxygen's got 8, this oxygen's got 8, this oxygen has also got 8. So all the nitrogens, or all the oxygens are happy. Notice though that the nitrogen has only got 6. So we need to give that nitrogen 2 more electrons. Of course that means we need to double bond, but where will we create the double bond? And it doesn't matter. We can go to any of these oxygens and take off 2 electrons. So I just removed 2 electrons from the oxygen on the left, and when I push those electrons into the middle, now if we take a look at our oxygen, it still has 8. Now our nitrogen has 8, they all have 8, and that would be the Lewis dot structure for NO3, remembering that the last thing we need to do is put this in brackets and add the charge. So that's how to draw Lewis dot structures. The last thing that you need to be able to do then is take these Lewis dot structures and figure out what these molecules actually look like. And I know that when you think about this, it gets a little overwhelming as you think about tetrahedral and trigonal pyramid and bent and straight and linear and trigonal planar and all of these different structures. Well, we are not going to ask that you know the names of these structures. What you do need to be able to do is link a Lewis dot structure with a shape. So first of all, let's talk about the shapes. This one should be familiar. It's got 4 points in 3-dimensional space. You may remember we call it tetrahedral, but whether you remember the name or not, this guy should be familiar. After this, we have a shape that we call trigonal pyramid. You'll notice that it's got 3 legs and that it looks kind of like a pyramid. It's not flat, but it's bent up a little bit. After that, we have a structure that we call bent that clearly looks bent. Following that, we have a structure that we call straight. Notice that straight only includes 2 atoms and 1 bond. So you'll find out that anytime we have only 1 bond, that structure is straight. In addition to that, we have this, which is also a 3-pointed shape. But you'll notice that it is flat. Again, you don't need to know the names, but this is called trigonal planar, and it is different from the one in the upper right-hand corner, trigonal pyramid, because the one in bottom left is flat and the one in top right is shaped like a pyramid. It bulges a little bit. Then finally, the last structure that we need to keep track of is what we call linear, and you'll notice that linear involves 1, 2, 3 atoms and 2 bonds. So what you've got to be able to do then is take Lewis dot structures and match them together with their shapes. So doing these in order, you will notice that this molecule, CH4, has 4 bonds. But if you look at all of the structures over here on the right, there's only one that has 4 bonds. So this has got to look like this. You don't need to know that's called tetrahedral. You just need to know that it looks like that guy. So now let's take a look at this second one. This second molecule has got 3 bonds. 1, 2, 3 bonds. So from the fact that it's got 3 bonds, that means that it either looks like this, because that guy in the upper right's got 3 bonds, or this, because the one in the lower left has also got 3 bonds. So how do you know which one it is? Well, the answer has to do with these unbonded electrons right here. What you're going to find out is that unbonded electrons make molecules bent out of shape. So this structure down in the lower left has 3 bonds, but it's very flat. It's not bent out of shape. You'll notice that this structure in the upper right also has 3 bonds, but it's bent out of shape. The reason is because there's an unbonded electron pair here that bends these guys down. But the bottom line is this guy has got 1, 2, 3 bonds. This has 3 bonds. The bottom left has 3 bonds, but we know that it's the one in the top right because this unbonded pair of electrons bends this guy down. The one in the lower left is not bent down, meaning it can't be that. Then looking at our last example, HF. Here we've got 1 atom bonded to 2 atoms. We only have 1 bond. Anytime there's only 1 bond, it looks like that guy. So we call this linear or straight. It's not linear, it's straight. We call this straight. You don't need to know the name. You just need to know anytime there's 1 bond, it's that dude right there. Looking at some more examples. We take a look, we take a look at NO2 minus. When we take a look at NO2 minus, you will notice that we have 1, 2 bonds. Notice that one of them is a double bond, but we still count it as one region of bonding. So we have 1, we have 2. So looking for ones that have 2 bonds, we've got this guy and we've got this guy. So it's either the one middle left or bottom right. But again, we have this unbonded pair of electrons, and unbonded pairs of electrons make things bendy. You'll notice that this one down here in the bottom right is not bendy, so it's not that one. It's the one here middle left, and if you want to draw them in, this unbonded pair of electrons bends these away, so this would be that guy. Now we take a look at NO3. You'll notice we've got 1, 2, 3 bonds. So if we've got 3 bonds, it again can either be upper right or bottom left. But now you will notice we don't have any unbonded electrons. Instead, we have 1 bond, 2 bonds, and then 3 bonds. Even though it's a double bond, you'll notice it's just one region of bonding. So we've got this guy upper right, this guy bottom left. But because we don't have any unbonded electrons there, it is no longer bendy, meaning that that is not it, and this is actually that guy. Again, because we've got 3 regions of bonding and no unbonded electrons, meaning this tends to be flat, and it would be the one bottom left. Now finally for this set, down here at the bottom, we have 4 bonds, and the only one it can be is that. Again, you don't need to know the names. You just got to be able to see what they look like 3-dimensionally. So wrapping this up then, you'll notice here we have, we could call either one of these carbons our central carbon, doesn't matter. But in either case, we've got one region of bonding here and another region of bonding there. That gives us 2 bonds. So this could be like this, or this could be like this. You'll notice though that we do not have, looking at our Lewis dot structure, we do not have any unbonded electrons on this carbon. There are no unbonded electrons, meaning this is not bendy. We see that this molecule is bendy. So because this doesn't have unbonded electrons, it's not bendy, and it looks like that guy down in the bottom right. Now contrast that with the next example. Here we have, again, 2 bonds, but now we have unbonded electrons. So looking at our 2 bonded structures, we've got this one or this one, but you'll notice now we have unbonded electrons. As we said, unbonded electrons make these bendy. The one in the bottom right is not bendy. The one in the middle left is bendy, so it would look like that. Then finally wrapping this up, in the bottom we've got 1, 2, 3 bonds, which would mean it's either top right or bottom left. But again, as you're figuring out, this guy has got unbonded electrons. Unbonded electrons make this bendy. And so if we look down here at our bottom left-hand guy, that's not bendy, that's flat. So that's not our guy. The one in the upper right-hand corner is bendy, meaning that that would be 3 bonds in bendy, and that's what this guy would look like. So those are the things that you need to be able to do to be ready for the remediation test. Going back to where we started, let's take a look here and remind ourselves of the 3 things that will be covered in remediation. You need to be able to identify salts and molecules. That is based upon their metal and non-metal locations. You need to be able to compare electronegativities within compounds simply by looking up the numbers. You need to be able to draw Lewis dot molecular structures, and you need to be able to identify their 3-dimensional structures. You don't need to know the names and angles. In order for you to move on from here, what you need to do is you need to complete the homework assignment that was posted along with this video, and again, check your answers. Once you have done that, you will have the opportunity to attend one of 2 Pride sessions. Regardless of who your teacher is, Miss Call or Mr. Knappenberger, you will go to Mr. Knappenberger's room either Thursday, December 15th or Friday, December 16th in order to get further remediation. In order to get into the room, you must be there by noon. If you're late, you will not be admitted. And in addition to that, you must bring your notes from this video and your completed homework assignment that was posted with this video. If you forget any of those things, you will also not be admitted, and you will forfeit your right to do the remediation test. During that Pride time, we will answer questions and offer further instruction. And upon completing the Pride time, you'll be given an additional homework assignment, which you will then complete over the weekend, and you will then have the opportunity to take the replacement test on Monday immediately following school. Your ability to get into the replacement test will require you to finish the assignment that you get during Pride. When you come to either one of those Pride sessions, Miss Call and I will both be there to offer more support and instruction, and we will move on from there. If you do have questions that you would like to address before Pride, please swing by your teacher's room before or after school, or make arrangements to stop by during Pride, just certainly not on Thursday or Friday because we will be doing other things. Thanks for spending time to get this information figured out. Good luck with this, and we look forward to seeing you next week.